one of the margarita sipping folks from DeepMind, Hubert, who'll be talking about AlphaProof.
Cool, thank you very much. Maybe some of you are surprised to see me here because I'm actually replacing my colleague, Alex Davis, who was supposed to come, but for personal reasons, he unfortunately couldn't join. I'm not sure exactly what he wanted to talk about, so we decided to talk about our own stuff, and so I'm going to talk about AlphaProof. In this talk, I've done a few talks recently. For those of you who've seen those talks, you will see half of it again, but for 30 minutes I'll try to do a live demo, so that will be a first. I haven't stress tested it, so hopefully it will work. It's supposed to work, but we will see. It's something that I've done actually with Alex Kuntorovich. I'll give more details, but I think he's coming in person tomorrow, and so you can validate with him that I'm not embellishing the story too much. And in this talk, basically the AlphaProof project started quite a while ago, actually in 2022. The goal of AlphaProof was never to only crack the IMO. The goal was really to see if we could contribute to research mathematics, and the IMO has always been a milestone. We try to use techniques that we think are not good enough only for the IMO, but that will go well beyond high school mathematics. And so the first part of the talk, I want to motivate kind of why we think that those methods are going to go much further. And there's a lot of the techniques that are inspired by what was presented in the previous talk, especially on the auto-formalization. All these are very important ideas for when you're trying to work with formal mathematics. Fortunately, I don't need to, in previous talks when I did it, for instance, internally, I needed to motivate mathematics, I needed to motivate formal mathematics, but fortunately, I don't have to do this here, and so that will leave us a bit of time for the demos. All right, so my talk is titled When RL Meets Formal Math, and so for those of you who don't know what RL means, it's a shorthand for reinforcement learning. And so reinforcement learning is what we believe is this very general kind of framework where you have an agent that interacts with an environment, tries to take action, and receives some reward and observation. Maybe what is important to know here is that often we think about, the reward has to be very precise so that it will guide the agent towards the right answer. But in fact, no, it's a very general framework, and the only thing you need to provide the agent is a goal. If you don't have a goal, then that doesn't really work. And so, for instance, if you want to encode how to make a great poem writer, that's very difficult to say this was a great poem or not without actually going directly, for instance, to a human. But if you can define, especially in a computer, how to say your goal was achieved or not, then you can use this framework and potentially scale it to make many, many interactions. So most RL algorithms work by learning two quantities. One is called the policy, which is basically a probability distribution over your potential actions. And often it's very useful to also learn this thing called the value, which is kind of a distribution of future returns, or in case where you achieve a goal or not, your probability of achieving a goal given the current where you are currently. And so recently, especially with the LLMs, you have this big return of, in some sense, I think it's called unsupervised learning, but in some form of supervised learning. And so I want to compare a little bit reinforcement learning and supervised learning and give you some ways to think about that. And taking the examples of the board games. So in Go and chess, supervised learning is, what you do is you'd learn by replaying professional games. So, maybe you buy a book of all the games played by kind of human chess players, and then you just read the book and you never play. That's supervised learning. And reinforcement learning is you actually learn by playing games. And so, of course, we have in our human intuition is that you actually need to actually play games because otherwise, you're not going to be really, really strong. And I guess I took this quote that I saw in one book from Paul Harnos, and that captures a little bit that intuition for mathematics. Don't just read it, fight it, ask your own questions, look for your own examples, discover your own proofs. So, like maybe it's insufficient to just read the work of other people and never try to prove anything yourself. That said, like the LLMs are, we have to admit that they are extremely successful. And so, maybe our priors of how we humans learn don't necessarily apply to machines. And maybe, they would be extremely good by just looking at, they're actually already pretty good by just looking at examples given by humans. Another way to think about this is that supervised learning is really powerful when the human data covers what the agent has to do, right? If you already have all the data in distribution, and maybe it's able to do the interpolation in between, then it's actually very, very good. But the advantage of RL or reinforcement learning is that you can also learn when there is not enough data or no human data at all. So you could imagine that could happen very easily in science. Maybe you try to solve a new problem, and maybe there is absolutely no literature about that, or maybe you're a mathematician and you invent your new theory, and then no one has written about that theory, and so you need to do things, learn on the spot on new data that doesn't exist, right? And so I'm a bit biased, but I'm going to talk about kind of this, what I call the zero series, which actually starts with AlphaGo, AlphaGo 0, Alpha 0, Mu 0, and Alpha Tensor. So I was very lucky to be able to work on this series of work. But in fact, there is no zero in the first work, AlphaGo, but this is really where everything starts. And maybe I'll share a little bit of a personal story, is that when I was quite young, contrary to many of my colleagues, I wasn't really trying to program things when I was 10 on the latest computer. Instead, I was playing a lot of Go. So I played maybe 10,000 hours of Go when I was middle school, high school student, and that took a lot of my time. And at some point, I had to go back to regular, studies. I did a bit of mathematics, but in fact, I owe a lot of things to Go, because my father, who is French, discovered the game of Go when he was a high schooler as well, and he got pretty good at it. He became a French champion and won a ticket to go to Japan like this. And he went to Japan. He actually did a thesis on AI, which is kind of funny, but more importantly, he met my mom over there. And so, in some sense, I owe my life to Go. And afterwards, right, like when I played Go myself, I studied math and engineering, and then I thought it would be a great idea to build a computer Go program with my dad, because that's one of the things he wanted to do at retirement. But then I realized that maybe another company was already doing that. And so I guess not only do I owe my life, I also kind of owe my current work to Go. And so I was very lucky. I was able to join the AlphaGo project. And then afterwards, we did basically this zero series. And so I want to illustrate a few things about AlphaGo. AlphaGo was actually a combination of supervised learning and reinforcement learning. And so it was a very pragmatic approach. Step one, you learn from human games and you get pretty good. And then step two, you drastically improve by actually playing games on your own, right? We had like some kind of, I would say, maybe it's a secret weapon, which was this search. So in most RL algorithms, there is no search. But here we had this thing called search that basically tries to evaluate the neural networks many, many times and aggregate information to make better decisions. And I want to illustrate this a little bit with the AlphaGo Move 37. That it will illustrate both the search and the idea of reinforcement learning. So this is a quote from Andrei Karpathy, who is not someone from DeepMind, but he said, let me read this. It's when an AI trained via the trial and error process of reinforcement learning discovers actions that are new, surprising, and secretly brilliant, even to expert humans. It's a magical, just slightly unnerving, emergent phenomenon only achievable by large-scale reinforcement learning. You can't get there by expert imitation. It's when AlphaGo played move 37 in game 2 against Lee Sedol, a weird move that was estimated to only have 1 in a 10,000 chance to be played by a human, but that was creative and brilliant in retrospect, leading to a win in that game. So the move 37 is actually this one. So we love to talk about this at DeepMind because but in reality it's well, it's one example of real creativity where, like human experts thought that, they actually thought when they saw that move that Agile placed the stone in the wrong place. They couldn't believe that that was actually the move that was proposed to AlphaGo, and when it was played, they thought it was wrong, and then suddenly, maybe 30 moves later, they realized that actually it worked pretty well. But we don't talk much about actually the power of search here, but I think it's a great illustration of search. Because if you agree that, this 1 in 10,000 chance is actually something that is well calibrated, then, are we really lucky? And, it's like we had a 1 in 10,000 chance we played that thing, and it turns out to be good, and that's, you just got lucky and you got creative. Actually, that's not what happened. It's like the search kind of estimate that was 1 in a 10,000 probability. It still had enough compute to explore that move. And then after exploring that move, it realized it was a good move. And then that's why it played it, right? And so if you didn't have a system that searched, then, like 9,990 times, it will be the wrong move to play, right? So that, I think, illustrates a little bit, like maybe some ideas that why the search is important. And so, okay, so the zero philosophy, it's not a Buddhism Zen philosophy, but it has maybe some similar concepts. Is the idea that, we took something and we removed all human knowledge, right? We remove like kind of what we knew about the game of Go. We remove all those features from the neural network. We remove all the things we had hard-coded about the game of Go. And we tried to see if, the agent could still learn to play the game of Go. And so it's really kind of, I think that it's a really amazing kind of research project, because if you're capable of mastering an environment from scratch, in some sense you have a system that is, almost by construction discovering and learning new knowledge by itself. This also means that it's a general algorithm, and maybe strangely, is if you can learn from zero, then it allows you to go to infinity. Is it okay if I take the questions at the end? Thank you. So we have at least, we had two big kind of results in this zero series. The first one was AlphaGo zero, and the other one was AlphaZero. Those systems learned by playing games against themselves, starting from random play. And so you see here I've shown two curves. So the y-axis is basically a measure of strength of the agent in Go, and in the x-axis is how much time it took to train that system. The dotted line is basically kind of the version that plays against Lee Sedol. So you could imagine that that's maybe top human play level. And so you can see that if you do supervised learning, then within the first hour of training, you already get a system that is really, really good, right? But somehow you are going to be capped at a certain level because you're training on a certain amount of data that is fixed, that contains a fixed amount of information. It's possible that with current technique, we would actually be able to build a stronger agent with that information. Maybe we could extract more information from the data, but there is an inherent cap of information in that data. Well, if you do reinforcement learning, in some sense you are generating your own data, and so you don't really have that cap. Of course, if you only have 1 hour of training, then reinforcement learning is a terrible idea. But if you have more compute, then potentially you can generate an agent that is going to be superhuman. And maybe one thing that was relatively surprising was that you could actually recover, when the two curves meet, so roughly, after 1 day of compute, is that already back in the day we had enough compute such that in 1 day you could kind of rediscover, all human knowledge in the game of Go that people have been playing for 3,000 years. And then after that, we could go beyond that. In chess, we had another illustrations in our paper of, like the kind of data that was rediscovered. For instance, we looked at openings in chess, and we plotted the frequency at which they appear during training. And so, for instance, here, one example is the Caro-Kann defense, and you see that the first 2 hours of training, like kind of the agent is never playing that, and then suddenly discover that thing, it plays it for a while, and then kind of it discards it as maybe that's not such a great defense, and I'll try to play something else. But for instance, the Queen's Gambit is something that is increasingly kind of appearing more and more in the safe play, and so probably AlphaZero quite like the Queen's Gambit. And we have like similar plots in Go of different kind of openings. So here in Go, it's called josekis. It's more like sequences in the corner. But basically, we could see really kind of knowledge being rediscovered and sometimes kind of discarded in preference of some new kind of discoveries. We also did this work afterwards. It's called AlphaTensor. So it's to illustrate that this kind of works not only for board games, not only for two-player games. So AlphaTensor was about trying to discover novel algorithms to multiply two matrices together. And so we had managed to transform like kind of the algorithm of matrix multiplication in some sort of a game. It's a one-player game, but it could be basically cast in the framework of RL, where the goal was to say, can you try to minimize the number of multiplications you need to do to multiply two matrices together? And so we discovered actually new algorithm, especially for like rectangular matrix multiplications. And kind of the bonus of this thing is that we could tackle huge action spaces. So in Go, okay, the number of actions is like 362. In chess also it's pretty limited, but depending on how you count. But here the action space was like 10 to the power 34. So for practical purposes, like basically infinite. And kind of, if you step back and try to think about what made those systems superhuman, I think there are like 4 points that are particularly important. One is scaled up trial and error, because basically it allows you to try many things, right? And then if you can do everything in silico, then you can make many experiments super quickly at the speed of machines rather than at the speed of humans. You need grounded feedback signal. Like you may try a bunch of things if you don't know if you succeeded or failed, or you have only maybe a biased outcome. Then you might learn something that is not quite true, right? The search I try to illustrate a little bit with our Move 37. I think it helps a lot in the exploration and kind of maybe making the algorithms much more efficient. And the curriculum is something that I haven't talked really about yet. But in Go and chess, because it's two-player games, we had this great thing called self-play, where you could play against yourself. And basically, you always play against an opponent which is exactly the same strength as you. Which is great, because imagine you are learning chess, but you only get to play against Kasparov, and he just plays full strength all the time, right? You lose all the games, maybe you don't learn anything, right? It would be really hard to learn from games where you lose against Kasparov if he doesn't teach you anything. In AlphaTensor, even though it's a one-player game and we didn't have this self-play, we kind of managed to, we had some ideas about the problem itself to create some kind of artificial curriculum. So let me come back to that afterwards. I just want to say that I've talked mostly about the things I was involved in the AlphaGo, the AlphaZero series, but actually reinforcement learning has been used in many other domains. So, in video games, but also, for instance, AlphaDev is basically trying to find kind of optimized sorting algorithm, and actually was pushed into the C++ standard library, I think the optimized version of sorting. There's also kind of work on applying to nuclear fusion, where you try to control kind of the plasma in a tokamak by controlling kind of your magnets and the intensity of the magnetic field. So I just wanted to say, if you can kind of, RL is this general framework where if you can if you have a goal, then you can try to optimize it. All right, so that was kind of previous work, and that was RL, and you see kind of the scaled up trial and error, perfect feedback, and then if you think about then kind of mathematics, then that's where you want to do it in formal mathematics, right? If you do it in informal mathematics, then you suddenly lose all kind of perfect feedback signal. And so when we discovered about lean, we thought that was like an amazing application for AlphaZero. And we had like this napkin kind of master plan based on the success we had previously, to say, well, lean is going to give us an environment and a way to scale up trial and error with an environment to explore mathematics completely in silico and a perfect feedback signal for proving. And therefore, outrageous conclusion, we can therefore tend towards super theorem prover and discover new truths, just like in Go, chess, tensor decomposition, etc., etc. And so if you go back to these 4 points that you need to check, right? Scaled up trial and error. Well, we have lean, and we have this AlphaZero agent that's going to go and try a bunch of things in lean. Lean is going to give you the grounded feedback signal. The search in AlphaZero worked pretty well, so let's reuse it. And the curriculum is really kind of the question to think about. And so if you go back to these two, like I guess I was pretty convinced that RL works. And so we really had to think about how do we generate kind of high enough quality and quantity of problems to solve a little bit this kind of this curriculum issue. Because obviously, like kind of, it's not really the case that for a theorem proving you have like a universal starting position that kind of generates all the other start positions. You need to really think about, like kind of what are the different problems you want to tackle, and you want to have many because you want to do this at scale. And so really you need to think about where do the problems come from. And I think kind of, the first answer is obviously that humans define the problems. And first reason is a relatively pragmatic reason, is that there are already a lot of problems that have been defined by humans. So let's go after that. But of course, like kind of also the goal is not really to do mathematics kind of in your, like who cares if kind of it's doing mathematics on its own, right? It's a little bit like kind of the tree that falls in the forest where there is no one. You don't really care. What you want to really do is to contribute to human mathematics. So you want to be in distribution of human mathematics for sure. And so again, to take that quote, right, it says you have to ask your own questions. So maybe that's also kind of a link to kind of the work on finding your own conjectures. And so we did a little bit of that, but in AlphaProof we had a lot of the problems were defined around human mathematics. So we used auto-formalization, and we use this thing called test time error. So I haven't talked yet about test time error, so it's okay if you don't understand. I'll come back to it. And of course, like new conjectures, you could think a little bit of that as like a little bit of potentially outside human mathematics. As long as it's helpful for human mathematics, I think would be a good metric. So just to recap that section, where RL meets formal mathematics, in some sense, we have a proven recipe in RL to build agents that can discover knowledge by themselves and reach superhuman intelligence in certain domains. The key ingredients were scaled up trial and error and grounded feedback. And basically, formal math provides us with those key ingredients. So that was the original kind of idea of why this might be very promising. Okay, I'll go a little bit into the methods of AlphaProof. A lot of the things are similar to that in the previous talk. But as it was said, the first thing you need to do is to train this, what we call the formalizer network. So basically, as it was said, right, most of the data exists in natural language. And so, you may have a problem like this, written in English, and you really want to represent it in formal language. And so we've used large language models to do this translation, and we are inspired by some of the work that was presented previously. The second thing you want is a prover model. So really what you care about is to prove things. And so this prover model in AlphaProof, as input, it takes kind of the lean tactic state, and what it's going to output is a proposal for the next tactics. So it might sample n tactics in parallel, and that are possible continuations of the proof. Then you're going to put these two things together. You're going to put the prover model inside of the search. And so the search is going to represent, where like nodes are going to be lean states, and the edges are going to be tactics. And so it's going to look for kind of possible kind of where to put the compute and where it's more likely to find a proof like this. So I've tried to illustrate it like this. And that search is similar to the search in AlphaZero that tries to exploit, high prior, what the neural network thinks is probably the best continuation to the proof. Things that, the value function thinks is maybe likely to reach the proof. So maybe even if, this was a 1 in a 10,000 chance, if the value says, oh, this is actually very likely, then we'll find a proof from there. It will be searched more. And there is also an exploration mechanism by even when the policy and the value don't think is great, we're sometimes going to put some compute there to explore, because sometimes, you need to come up with new things. And so if you take all these ingredients, then kind of the recipe is something like this. Step one, you do auto-formalization. So you train a formalization model and auto-formalize human-created problems. And so I've tried to make a little illustration of this, where you have the human problem in the middle, and then the auto-formalization is not always perfect. It's it's going to create things that look like the human problem. For certain things, it's going to be very good, and it's going to exactly kind of formalize things. But sometimes it's going to make some approximation. So maybe it might drop a hypothesis, or it might not exactly translate the thing. But the great thing about being in Lean is that as long as you pass the syntax check, then you have a well-formed problem. It might actually be false. It might be trivial. Sometimes it's actually interesting, even though it's not the original problem. But these are all valid problems, and so you can learn from either proving them or trying to disprove them. You can try to learn something. What we did is we found about 1 million informal problems, and we auto-formalized them into a big data set of about 100 million statements. And then the next step is about trying to generate proofs for those 100 million problems. And so how that works is first we build on top of MathLib. So if you take the prover model, like a pre-trained model, hasn't seen a lot of Lean, has never seen kind of Lean states, it might not be very good at kind of trying to complete the proofs. So we basically took the MathLib library and we created state tactic pairs, and then we train our prover model on this. So we take a state that is part of a human written proof, and we train towards the human tactic. And so there is about 300,000 lines of proofs. So you can imagine there is about 300,000 state tactic pairs. And in this way, it learned many mathematical concepts, actually many research-level mathematics concepts. But for the IMO, there is a lot of things that is missing, because the IMO is quite out of distribution compared to what is in MathLib. And so you will need to train your prover model to do well for problems that are like the IMO. And so that's step 3, where this reinforcement learning pipeline comes in. So the previous pipeline is really like AlphaGo. You learn from human data. There's a supervised learning phase. You get a model that already knows how to do stuff, and then you drastically improve it by doing RL. And so for each formal problem, you're going to generate experience of trying to either prove or disprove by searching over Lean steps. You're going to use Lean to verify whether you've actually proven it or not, or you've actually disproved it or not. And then you're going to reinforce the prover network with each success. So you can learn from disproofs and you can learn from proofs. It's really hard to learn from things you haven't managed to either prove or disprove. A little bit maybe a little bit like you play against Kasparov and you lost, and it's hard to tell where really where were your mistakes. And I try to illustrate a little bit what kind of the main RL thing does. So of course, this is supposed to represent the problems that the agent can solve after learning from MathLib. So obviously, it's like super highly dimensional. So don't take it too seriously. It's just kind of illustrative. But basically, you have this first sphere, and then you have the sphere of problems that you've auto-formalized. And so it looks pretty different. I wanted to illustrate kind of the problems you care about to be able to do well at the IMO is quite different from what you have in MathLib. But you have some problems that are like close by. And so what's going to happen is that when you're going to solve some of the problems that the initial model can solve, you're going to learn from that. And then it's going to expand a little bit its capabilities towards the other sphere. And then little by little, it's going to learn about how to prove those things, and it's going to learn from those proofs, and it's going to help it to prove the next things. And so you are very great, but what if you get a problem that is very different from the ones you've trained on, that is kind of out of distribution? And so if you know a little bit about the IMO, actually a lot of the problems are chosen this way so that they are kind of adversarial to memorization. I think there is a whole committee that when people proposes the problem, they try to figure out if a similar problem was given in the past. And so it's really selected to be adversarial to memorization, at least I would say for humans. And so to do these kind of things, we have the last thing that we call the test time RL. And so the test time RL, it has a graph that is pretty similar to the one I was showing in the previous talk, maybe, but it goes in the other direction. And so basically, the test time RL is the same process as the main RL, but instead of learning about the problems you've auto-formalized, you're going to you have a target problem you want to solve, the IMO problem you want to solve, and you're going to try to generate variants of that problem. And you're going to try to learn by proving those variants and kind of climbing your way up to the problem you care about. But otherwise, it's the same the same RL step as the main RL. And so the illustration looks like this. So at the bottom, you have what the agent can do. And then over there, you have the very hard problem. And so first, you try to generate variants of that problem. You use a large language model to do that, and you blow up that problem in all directions. And then if you've generated kind of problems with high enough density, and there are problems that maybe the agent can already solve, it's going to do this thing where it's going to learn a little bit about that problem, that variant, that's going to push its capabilities towards the very hard problem, and it's going to continue to do this until hopefully you reach the problem you really cared about. So that's test time RL. And so in that, you have a bit of conjecturing, but it's a conjecture that is conditional on the problem you want to solve. So it's a bit different. It's very different from theory building, where in some sense maybe you would expand in some direction. There's not a particular problem you care to solve. You just want to build a new theory. So that's a bit different. The challenges for AlphaProof is, first is we inherit the challenges of formal mathematics. So most of human data is in natural language, and as was described in the previous talk and in this talk, we made quite a lot of progress in auto-formalization, and so there's progress being made here, but still it's still a big challenge. The second thing is, and that's more like problematic, is that it's very hard to learn and work on areas that are not supported by MathLib. So I don't know, like for instance, if you are asked to solve a PDE and there is no notion of partial derivatives in MathLib, then it's going to be impossible for AlphaProof to do anything about that, right? And generally, like kind of creative building of new objects and theories, interestingness and the beauty in mathematics, that's something we haven't done at all in AlphaProof, and maybe that will be part of future work. I just want to say very few words about the IMO 2024, because I actually want to do this live demo, and I think I will need 30 minutes to do that. So just I wanted to, we tried to participate at the IMO 2024, and I just want to, like kind of say what was actually really our goal. So our goal was, I would say it's more like kind of like an Apollo program. Can we reach the moon, and can our system solve those problems at all? Can we, of course, like the reality is that we use more compute than is available to humans, more time, etc. But we wanted to see if we could do it at all, right? And then once you can do it at all, then how you can optimize your system and try to make it more efficient, etc., etc. We hadn't reached the level where we could do it in 4.5 hours. Wanted to see if we can solve any problem at all. And so in some of the other talks, I go a little bit more and tell a little bit more the story of what happened at the IMO. But I just want to say so the final results we got, that maybe you may be aware, is that AlphaProof was able to prove P1, P2, and P6. For the geometry problems, we were partnering with another system that was developed within Google that's called AlphaGeometry. Partly because, at least at the time, there was very little support in MathLib for, again, IMO-like geometry problems. And in terms of score, so that kind of gave us 28 points. And so we reached the score of a silver medalist. Unfortunately, missed the gold threshold by 1 point. And of course, I want to repeat, we use way more time and compute that would be available to humans. Some of the challenges is we suffered a little bit from the gaps in MathLib. The most obvious one is geometry. Like ideally, we would have also done geometry. We had one system to do all the problems. I have even P1, that's maybe a story for another time. The combinatorics problems were really difficult. Actually, P5 were extremely hard to formalize. We failed to formalize it the first day. I'm not even sure we have a version that we think is exact representation of the problem today. And the reality is we did not make any progress on P3 and P5. We were hoping to make a progress on P3. We had proven a little something, but that was not enough to get a point, unfortunately. And of course, as I said, we use many orders of magnitude more compute than human consistence. But from our perspective, we kind of successfully landed on the moon. But if we are going to do this trip another time, we would really want to be way more efficient. All right, so that's now, I want to go into the live demo, which is the new thing. And I want to say many thanks to Alex Motorovich. So I just want to tell you a little bit the context of this demo. So I had the opportunity to go to the US. Recently, we were invited at the IAS. And over there, I met Alex Motorovich. And he said, I want to show you how I work. And I wanted to see if, AlphaProof could be useful in the work he was doing. And so we went to his office. He showed me one of the theorems he was working on, the next theorem he was going to work on as part of his prime number theorem kind of formalization project. And we tried to see if in there, AlphaProof could do something. And so we had a setup where we wanted to try is AlphaProof was going to, we're going to, we have this AlphaProof thing that can actually, obviously do things when you give it a lot of compute, but it can also actually do a lot of things even with very restricted compute. So obviously, I'm not going to ask you to wait 3 days for these things to come back. I hopefully can do it pretty quickly. So it's, in some sense, if you want, it's like AlphaProof Mini, and let's see what AlphaProof Mini can do. And so the next problem that Alex was going to work on, and he picked that especially for us to work on because it's pretty self-contained. You don't need other results in his kind of formalization project. Mathlib knows all the results you need to prove this thing. And so it's this lemma zeta 0 free const. And so basically, what does it say? It says that for any y, there exists x such that kind of in that slice there is no 0 in the Riemann zeta function. So that's cool. And kind of the proof goes by a contradiction argument. And so the way we started is we said, okay, let's try on some simple lemmas that Mathlib already knows about. So okay, so one result that Mathlib knows about is that on the one line, so when on this kind of when the real value is 1, then there is no zeros in the zeta function. So we have this sorry, and then what we can do is, this is kind of an internal thing, but we can try to call AlphaProof on this sorry and see if it's going to return or not. So this thing is going to take sometimes, it's going to take 2-3 minutes. Sometimes it comes back very quickly. For this one, it should return pretty quickly. Okay, so it did this thing, is retrieved. Okay, so it loves to do this thing that is completely useless at first. It's probably useful for it, but not useful for you. Okay, so it basically retrieved the theorem that is in Mathlib that you want. Riemann zeta not equal to 0 of 1 LERE. So I imagine that exactly what you want, right? If you look here, no, it's like 4 in the case where the real value is bigger than 1, then there is no 0, so it applies in this case. The other thing that we said is that the zeta function is continuous everywhere apart from the point that is 1. So again, I think that's a result in Mathlib, and so if we call AlphaProof, hopefully, it can retrieve that theorem and kind of use it in this lemma. So let's see. That's the moment that is a bit stressful. Okay, cool. I mean, that looks like kind of, I'm really not an expert, but that feels like kind of probably the right theorem to use. Differential at Riemann zeta and kind of using this continuous at property. Okay, great. So now let's go to the real thing that we did, this zeta 0 free const. And so the general proof strategy is to do a proof by contradiction. And so the way it worked is that Alex wrote the steps of what he had in mind, right? He said, okay, first we need to do by contradiction. So he wrote by contra h, push negative h, which basically means let's do a by contradiction argument. And so where we are here is that so the comments is what I've added afterwards, especially as I went back to the proof and made sure I understood it. He says, well, okay, so we therefore know that for all x smaller than 1, there is a little x and y in that slice, such that you have a 0. And we're going to try to find a contradiction with that. And so he said, okay, that's also written by Alex. He said, okay, let's pick, big X being 1 minus 1 over n plus 1. And so basically, we are going to get really close to this one line. We are going to have a sequence, and then that's going to converge to someplace in the one line. And then we're going to take the limit and say, well, we're going to find a 0 on this one line. But obviously, we know that there's not supposed to be any zeros on that one line, and that's how we're going to get to that contradiction. So I've defined all these things, and so, okay, this is also written by Alex. He says, okay, let's, like now that we've picked x equal 1 minus n plus 1, then we are going to pick the xn and the yn, that we're going to define those sequences. And the first step he said is like we're going to show that. So we're going to try to show that this xn converges to 1, which is kind of, it's supposed to work well. And the first step is to prove that xn is smaller than 1. So that's not completely obvious that xn has to be smaller than 1. At least, when I went back to the proof, I wasn't sure how to prove that. It's actually the fact that we know that there is no zeros post 1. So hopefully it should use that result to say, well, we can assume that xn is smaller than 1. So that might take a little bit of time. So let me take you to the next step. That once you know that it's bigger than 1 over 1 minus 1 over n plus 1 and 1, then by the squeeze theorem, you should be able to prove that it converges to 1. So that's how you do it in Lean with those filter things. And so we can call AlphaProof while it's working on the previous story. We can call it, came back. Okay, so it uses the theorem about there is no zero post, the one that we saw before. It's tried to use some tactics that I guess comes with some Squiggly mark. We don't restrict it for anything. And then afterwards, it came back with this kind of the proof of I guess, it should be using the squeeze theorem, or something similar to the squeeze theorem. Actually, I don't know if any of you can spot it, or maybe it goes directly. I'm not quite sure. But okay, so now we have something. We have this sequence that converges to 1. And then we are going to say we're going to use a compactness argument. So that again, all those half statements are written by Alex. And incredibly, he didn't make any errors in writing this. So he was like, okay, then next, we're going to define this subsequence. And so, by compactness, we know there is a subsequence such that, it's going to converge to a certain y0. Okay. So that now we are working on kind of the, we worked on the x. We know it converges to 1. We are kind of setting where it's going to land on the y-axis. So it's going to land into a y0. So while it works on that, we can go to the next things that are fairly easy. Now that we have this subsequence, okay, sorry, it's working well. Now that it has proven that there is this subsequence, then you can say that xn on that subsequence is also going to converge to 1. That is fairly trivial. Nothing special there. And then the next step is going to say, okay, then we're going to take xn plus yn on that subsequence, and it's going to kind of converge to 1 plus y0 complex I. And so here there is a subtlety, is this neighborhood thing. So it's not just pushing the limit. Maybe some of you can actually explain me exactly what that means. But that makes this kind of this lemma slightly more challenging for AlphaProof. But basically, yes, kind of the result is xn is going to go to 1. We'll have that, and we just said that yn is going to go to y0. So hopefully, it should just converge to this. So this again is written by Alex, and then we can call on that one, which is this. Okay, it came back very quickly this time. I'm a bit lucky. That the zeta function is 0 on the subsequence. That's basically one of our hypotheses. We had the hypothesis that x plus yi was 0, and then we just say that it's also true on the subsequence, which is mostly one of our hypotheses, so it should go fairly quickly. And so here okay, so you see it's what so here we are there, and so when we reach that point, we're like, okay, well, we almost have a contradiction. We're done because we have this zeta function defined on the subsequences. that is supposed to be, that is going to be 0, and we know it cannot be 0 on the one line, right? Like xn is going to converge to 1. And so we launched AlphaProof there, and then it took a bit of time, and so we are thinking, why is it taking time? And then Alex said, oh yes, like there is a step missing, is that actually kind of, what you want to do is to take the limit there, but zeta is not continuous at 1. So in the case where, the yn converges to 1, then you need a slightly different argument. And so that's why we say, okay, we actually had to case on the fact that y0 was 0 or 1. In the case where it's 0, basically you get the argument because zeta blows up, and so it cannot be 0. And in the other case, you are going to finish it by continuity. And so the way it worked is, like kind of AlphaProof was responding kind of quite quickly like this. And sometimes, it was a bit stuck on something. And then Alex would say, okay, let me just write another half statements that would decompose this thing in two. So I can't remember exactly. I think that's why we have like these extra half statements there, where when we called AlphaProof on the by cases y0 equals 0, it didn't respond in the first 2-3 minutes. So we said, okay, let's kind of make some smaller steps for AlphaProof. And so, it's, at least for Alex, it was very easy to write those half statements. Like, surprisingly to me, he wrote all those half statements without ever making an error. Like you could easily, I think, write one of those half statements and be a false statement, and then you'd be a bit stuck. Okay, so it used this theorem, Riemann residue 1. That shows it that it's supposed to blow up, and then of course if it's blow up, it's supposed to be non-zero, and then after that it's going to have a contradiction with the fact that it was 0. So let me launch these two together. There we have them. In the other case, we are going to use the fact that zeta is continuous and finish the proof like this. So let me actually go there and ask AlphaProof to work on all the stories. So that was kind of a little bit our experiment with Alex on the first day. And so to do all of this, it took us about an hour and a half. But I would say a lot of the time was spent on, well, maybe you can ask Alex what this time was spent on. So we had like this amazing experience the first day. And so we said, okay, let's do another one the next day. And I'm not showing you the next one. And why is that? Is that actually, so we took something that was less, that relied on some of the results that is already in the prime number theorem kind of project. And so Alex said, oh, but actually we don't care about all of this. What we need is that this Van Mangold function is just like kind of upper bounded by log n. And we try to extract a lemma. And we are like, okay, let's repeat this experiment. And we call AlphaProof on, actually we didn't scaffold anything at the beginning. We called it on the first story to see if it could do the whole thing. Unfortunately, it disproved the statement. It said the statement is false. And we spent about 2 hours trying to fix the statement. But each time it disproved the statement. So at the end of the 2 hours, we still had a false statement. And we realized that was probably not the right strategy to fix the statement. We thought it must be some silly things, but we couldn't actually really fix the problem. So one of the things that AlphaProof will do for you as well is that in case you have a statement that is false, it's at the same time trying to disprove it. So it will tell you, you've made a mistake there, and then you have to read what comes out of the proof and say, where is the mistake, right? And so one thing that is usually quite nice is you can copy that and, like, for instance, put it in Gemini and say, what might be the problem there? And sometimes it comes up with something useful. But kind of our conclusion was that it would have actually been better, instead of trying to fix the statement, to continue write the proof that we think was going to go through. And then at some point, it would have been clear exactly what was the problem in kind of the formulation of the lemma. Yeah, so we are almost done. We've done all the stories about the last one. And so the last one, yes, so now we know that zeta is 0, and so it should be just kind of fairly obvious how to finish there. Sometimes it takes a bit of time, but that was our experience. And so he's going to be there, I believe, tomorrow. So you can really ask him more about this. We've only tried 2 things. I'll be really keen to try more things, see what it can and cannot do. In the meantime, we'll come back to this at the end to make sure that there is no stories left at the end. Let me go back to my presentation. So we had also prepared a few other we're trying to explore what AlphaProof can do. And so this is about PDE. So we're investigating whether, how would it be to get it to do some stuff about PDEs? And maybe you should ask Paul Lezo over there next to Kevin, who did all the work in Lean and in our internal version of Mathlib, to see how fast can you learn something that is not there in Mathlib. And so Paul was able to add enough stuff in Mathlib and kind of AlphaProof learn about that thing to be able to basically use the methods of characteristics in those quasi-linear PDEs. And so at the moment, I think, Paul, you started a chain of PRs to put back the things we've done internally back into Mathlib. So that was a relatively positive experience to see that actually, even though it doesn't exist in Mathlib, if you do a bit of manual work, then you can get it to do things. So that was pretty cool. Another thing that we saw is that, so in this paper that was accepted at the ANAS from Alexander Logunov, there is some kind of technical lemma there. And so again, it's Paul who made the work of scaffolding it and putting in the stories. And so actually all those stories you can complete with AlphaProof in the same a few minutes of things. Cool. So a lot of this thing is the work of a whole team, and maybe that was a very important thing is that to do this kind of project, at least in my experience, it's a little bit like in mathematics. I've heard that you need to be very optimistic that you're going to find a proof, because if you're pessimistic, then there is no chance you're going to make it. And so I think that was one of the strengths of this team, and actually I think it comes from all the way back from the AlphaGo days, is that we are not thinking we're going to fail. We're thinking, yes, we're going to make it, and even though maybe 6 months before the IMO, if you came in and you look at what AlphaProof could do, you'd be like, these guys are a bit, maybe they're smoking, but in a lot of things, you do a lot of research and then you put everything together, and so it's really hard to see exactly what is going to be the trend of the curve. But it's the work of many fantastic people. So yeah, these people are unfortunately the people who left Google since then, and so there's not their picture anymore. But we had a lot of help from a lot of people within DeepMind, and from some of you here as well. So what's next? I want to touch a little bit on what's next. So as I said at the very beginning, the goal of AlphaProof was not to crack the IMO really. The goal was to see if we can contribute to mathematics. I guess it's maybe we can't contribute individually, but we are pretty good at training machines and may be able to contribute. And so we need to broaden to the entire mathematical landscape. And so especially when we are back in July, it was really good at high school stuff, but can it do some more undergraduate stuff, graduate level things? And so maybe with the demo you can see that, okay, this is not super advanced mathematics in the sense the proof is that I understand the proof. It uses some easy things about limits and compactness and subsequences and things like this, but still I think it's probably undergraduate level math, and so it starts to be able to do these kind of things. If we can make AlphaProof as a useful tool for you guys, obviously, but also maybe for non-professional mathematicians at some point, can they use proving as part of their work? That would be something fantastic. So I want to touch a little bit on some of the stuff we've done recently, because I've told some of you, DeepMind strategy has always been to work a little bit in a submarine mode, where for a while, you don't know at all what we are up to, and then suddenly, boom, we come out with, a match against the world champion at Go, or, maybe trying to participate at the IMO and doing not too badly. But I think that this phase of the project was very useful. It allowed us to focus and maybe do a little stunt. But I think that we are in this new stage where we would really like to open up and contribute back to the community. And so our first step in doing this is this data set of formal conjectures. So we had done some work to formalize quite a bit of problems on our own. So we had like about 160 open problems and 130 solved problems. And we thought that that would be much better if it was part of the community. And so we asked advice from some of you, Floris and Kevin and Bavik and Johan, to see if that would be of interest. And so about, I think it's 2 weeks ago, we released that open source. And so it's a repository of formal statements of conjectures. The goal is to clarify their meaning and help maybe expand mathly. And of course, it might serve us and other kind of AI place as a benchmark, but it might also serve you as an understanding of where AI is. So of course, we'd love if you are interested in it. And I personally think that kind of the best version of this data set if it's owned by the community. So I think we'll do a lot of work at the beginning to see if it gets any traction and help push it. But at some point, I think it would be better served if it was part of the community. So, but I have to say, we had already quite a few contributions. So thank you very much. It has currently, maybe the 30, maybe like something like 70 more problems. So quite a lot more problems. I think a lot of them are like very famous conjectures. I don't know, Kevin, if you put the Fermat's theorem in it, I guess it's not an open problem anymore. It's kind of a little joke. So yeah, formal conjectures is one of such things. The other thing, the demo I showed you, this is an internal version, but we are working very hard to make it available to every one of you. So we may, I think it will go first in a period where we try to figure out what it can do, what is the best way to interact with it, etc. So my interaction with Alex Kantorovich felt like this is a great starting point, but it's a bit anecdotal as well. We tried two things. The first day it worked great. The second day we disproved the statement for 2 hours. And so like what are the best ways to use these things? I think that would be really cool. And to finish, as part of this formal conjecture kind of data set, there's a lot of problem coming from the erdishproblems.com, which is a website that is maintained by Thomas Bloom, a fantastic website. So it's been like great for us to kind of start to build that data set. And as part of that, there's a problem, this problem. And it was written that the answer is yes, as shown in this paper by Baumgartner. And so what we did is we formalized a bunch of these problems, and then we tried to find maybe misformalizations in those problems. And so we ran AlphaProof on trying to disprove every formalization we made. And so it disproved that theorem. And so we are like, oh my God, no, there is an error in the formalization. But it turns out that, in fact, there was just an error in the reporting. This paper proved that the answer is no. And so we went back to Thomas Bloom, and so now if you go to that webpage, the answer is no. And maybe what was interesting is that AlphaProof had found a different solution from the paper. It came up with an explicit construction of this silence set. And so if you go to the website, you have that. So yeah, I think that was my last slide. So our hope is to be able to contribute back to the community and be part of this community, kind of continue to contribute to research math, and maybe one day to find a proof that is part of the book. Thank you very much.
Okay, let's see. 1, 2, 3, 4, 5, 6, 7. So remember your number.
Was I one? Yes. So it seemed that the actual way that the proof is sampled is line by line, essentially. Would it be very tricky to also let it do this kind of scaffolding, where it first comes up with like a skeleton with stories in there, and then goes back to the stories and expands on it?
No, it's totally doable. I think that depends a little bit, like for instance, that's the idea behind draft proof sketch. For instance, it's a great idea. I think maybe potentially kind of one of the things you would have to think about is what if one of your half statements is actually is false. then you can prove everything afterwards because this is false. But you need to come and fix the thing. So you really need to want to have something that edits the proof, but it's totally, I think, a very interesting direction.
In the RL loop that you had, so the agent is an LLM, and the environment is the lean proof system, correct?
Sorry, yeah.
So in the RL loop that you were using to train the
Yep.
LLM, the RL agent is a LLM, and lean is part of the environment, correct?
Yeah, exactly, yes.
And the feedback signal that you provide, does that simply say the proof generated by the LLM is correct or incorrect? In other words, is it just a Boolean feedback, or is it more fine-grained than that?
So there are like two feedbacks. The first feedback is kind of what does the lean tactic state look like? So at every time you write a line, this lean tactic state updates. And so the agent sees that after every kind of line it submits to lean. But at the end, yes, it only sees 1 or 0.
So we had written a paper very similar to this, but in the context of physics and chemistry, where we provide fine-grained feedback. That's much more effective than Boolean feedback.
Yeah, so I think if you can come up with kind of fine-grained feedback, then it's for sure it's going to be way more efficient. And so that's kind of that's what you want your value function to learn. So if the value function can start to learn, am I on a path that is probably going to lead to a proof or not? That might give you this fine-grained kind of feedback. Of course, if you can inject that also kind of in some sense manually, or kind of extract that from the environment, then you should. Yeah.
Can you say something about how you generate the test time variance?
Yeah, this is generated by kind of a large language model with few-shot prompting.
I have two questions. First,
I think we're going in order. So, who did I have as
number 4.
Okay,
Sorry.
4, okay.
Two questions. First, when can we see the nature paper? Because I've been waiting for a year.
The AlphaProof paper.
Yeah, the nature paper, I assume.
So yeah, we actually, hopefully, you should see that fairly soon. So.
Second question, what do you do for diversity in the alpha? Do you use anything beyond temperature sampling?
For the diversity in which where exactly?
When you're generating the first the alpha statements, and second the tactics.
Sorry, it's like when we generate the formal statements or when we generate the tactics?
I mean, in both cases.
In both cases, yeah. Nothing very kind of crazy. Yeah, just kind of temperature during sampling. Yes.
So who was 5?
I think I was 5. So first, maybe you want to check whether the proof is finished.
Let's go. Let's go check.
Could you just clarify? So this is all running in a faraway server, so it's not running on your computer.
No, it's not running on my computer. Yes. So it's finished, right?
And you know for sure that it did not learn from your previous session with Alex?
Yeah, I can. You'll have to trust me, but I guarantee that. It's the exact same model that I run. Yeah.
Okay, and the question I wanted to ask was, so in the IMO stuff, so the proof were taking some unnecessary step or had this, I don't know, crazy induction or whatever it was. Can you comment a bit on that? Because you didn't mention that at all.
Yeah, I think you saw it in the first thing where it tries to do this boralized thing, or sometimes it inhabits something that even me can spot that that's a totally useless step in the proof. I have some idea of why it does that. I think it's actually useful for it to prove the thing. And so the reason why is that, so we, as part of the process, we tell AlphaProof that it cannot do an action that will be a no-op. So if you take a tactic that leads to the exact same lean state, it will be rejected. And so I think as part of the things it has learned, it has learned to output an action that is not going to be a exact no-op, but that is going to be kind of a no-op, so that it can, in case, say it generates, n actions at a time, in case, and they always sample something that is kind of safe, is my interpretation, so that it can resample another set of actions. So I think that actually, if we change a little bit, if that's the right intuition, then there is a way to change a little bit kind of that. Let AlphaProof resample when it wants instead of kind of coming up with this kind of dummy action. So well, other way, we could add a dummy action called resample, and then when it kind of goes through that thing, we just don't show it to you. But that's my intuition of why it's doing it, because it's kind of incentivized to try to generate fairly short proof in its objective. So that's one explanation, but I haven't gone to the bottom of it. I think it's probably something that is useful for it. So if we remove all those things, it might hurt performance.
So you're working on getting rid of those or having proof that could be helpful to humans?
Well, I think, if some of the stuff, yes, it's like, and so there is another question about, is that a proof that, you would actually submit to Massive or not? And probably, maybe not, because like if like maybe there are considerations or you update lean, you update massive, and how many of those proofs are going to break, etc., etc. So we haven't optimized at all for kind of the elegance of the proof. I think that's actually a great job for a large language model, because you can tell it, just generate me that proof in the style of a human lean expert, and then you can iterate, like given kind of the already a proof that already works, right? And then you can loop and verify with lean that the proof still passes. And so these kind of things where it's more like, I don't know, my interpretation is like more like style. I think that's a great job for things like this. So maybe it's very important, and when we make this kind of tool available, maybe that should be one of the final steps that is done, possibly. So I think I'd love to hear that feedback, and like not everything has to be decided on day zero, but as we go, make it more and more useful. Yeah. But I think it probably has a lot of the right ideas. It might not be the way you would write it, but I think that once you know which theorem you want to use or what is roughly the technique, then that might work really well.
Okay, who was 6 and 7?
My question is about a sort of proof of the sequence 1 plus 2 plus m to infinity is equal to minus 112.
Okay.
Yeah, this is a complicated joke,
yeah.
Actually. And can this system generate this sort of proofs? Then you need to find some sort of non-standard assumption inside the proof.
So
yeah, you have to assume all this 1 minus 1 is equal to 1.
So I know kind of the sketches of kind of this thing. This is like using analytic continuation, I think, of like minus 1 over 12, and maybe it's, I imagine that it would be a proof that would be rejected by Lee.
Yeah.
And so which part were you really curious about? Like,
yeah, how it would react to such proof. It's not really standard because you have to agree that 1 minus.
Okay, so what if our AlphaProof system could look at a informal proof and generate a formal proof, right?
Yeah.
And then maybe you show it this proof of kind of packaging the ones and the minus ones in kind of the correct way, and then it comes up with some, and then kind of it looks strange. So I think it might try to. So we don't have that system today. So like you can input it. It doesn't take into account, for instance, the comments I've written, etc. That's the only thing it sees is the lean tactic state. So we can't actually run that experiment. Of course, I'd imagine that for a lot of even for a lot of informal proofs, they're actually slightly wrong, right?
Yeah, it's slightly wrong.
So slightly wrong, and so if you try to formalize line by line, I think you are going to end in a dead end, because like any single little mistake is going to be a problem. So what you want is to have something that is fairly flexible in kind of understanding the idea and kind of writing the proof itself. In the case where the whole thing is wrong, then I don't have anything interesting to say. I think it will just unfortunately be rejected by Lean, and I doubt it will emit a comment saying this is, yeah.
Last question.
So, in this demo that you developed with Alex, so it seems to me that you have comments, well, either written by you or by Alex. And so the question was whether it was, first of all, if AlphaProof was able to use these comments, So in the sense that if you can help a little bit, if you, like saying, oh, but come on, you're just trying this limit in something or another. And the second thing, well, I noticed that, well, since Alex, he's an expert in Lean, so he formatted the statement in a very precise manner. So the question is whether it would have been so efficiently, even with somehow correct statements, but stated in a less aligned.
Yeah, okay. So your first question is about the comments. I think, like that would be a great feature. At the moment, AlphaProof only sees the lean tactic state. So the way we kind of helped AlphaProof is to write intermediary half statements. Say, oh, like, hasn't responded in the next 2 minutes, like the last 2 minutes. That's actually, I'm just going to write a half statement, cancel the previous request and launch it new, and then it will go faster than waiting potentially, right? So that's how we helped it, is directly in formal language. But absolutely, right? Like if you knew that, like maybe instead of writing half count at zeta count, you could say use continuity argument. That would have been cool too, right? I think that's a great suggestion for the future. And your second question is, yeah, kind of. I think like kind of. Alex is definitely one of your kind of lean experts, and he's really proficient already at writing those half statements, right? And so like he could easily made a mistake, but actually just wrote the whole thing, like kind of said, okay, next idea is this, and then he expressed this very quickly in lean. And so absolutely, I think for people who are kind of less experts, kind of what would be fantastic is to have like the auto-formalization model as one of those tools as well, where you write kind of the description of the half statement you want to write, and then you say go, and like it will come back with something that will not always be true. But then I think there is something interesting is that if you imagine you have your top statement that is, if you can imagine your top statement is correct, then that grounds everything that comes afterwards. So even if the AI makes a mistake in the half statement, at some point you will hit a problem, and then you will be able to iterate and kind of fix. But obviously, kind of auto-formalization of statements is actually extremely hard. Like every little mistake is potentially problematic, but I think it's a great suggestion as well to have that as part of the tools that kind of it can give you, and then you can help you write that half statements, and maybe you spot some errors and kind of iterate.
That's true, but I was also asking for something perhaps less ambitious. Which, for instance, at a certain point you had a limit statement that something were convergent to something else, and Alex rightly proposed to state it in the terms of filters. Here on line 96, yeah. I think for almost so that for well, it doesn't matter. Yeah, exactly. This statement is stated in terms of filters, so it's stated in a very markedly compatible manner. So my question was whether if you state the same statement, so it is a correct one, by using, for instance, epsilon and delta or something. So it's not really auto-formalization in the sense that it is it's a correct statement written in lean, a right statement, but just not.
Yeah. So I would say why not, right? Like, maybe it would have, I imagine it would be able to do it as well, but we haven't tried. And it's like, this is really what came out of kind of Alex's hands when he was typing it, and so that's what I've been trying to show. The comments I added myself when I went back to this proof, try to make sure I understand it. I slightly changed the notations as well. He was using sigma and t, which was hard for me to interpret. So I used x and y, but that's about it. And so yeah, you can ask him tomorrow about his experience.
So I want to build on that question. So I imagine that there's probably more than one instance, right? Actually, maybe you can answer this one first. Are there instances when it does express things? So if it does express something in like a non-MATLAB compatible manner, oftentimes it's possible to translate via, like if you express something in terms of filters and epsilon deltas, and you'll have, obviously if it's compatible, then you'll have an if, you'll have a rewrite lemma somewhere. So does it do these, do you think, or has it ever done things formalized in a non-MATLAB compatible manner directly, or would it translate and then sort of use MATLAB stuff and then translate back or something like that?
So the auto-formalization, we've looked at it a lot in the context of the IMO, where the math knowledge that you need is fairly limited, and so and it's trained on kind of using MathLib. But I think it's going to be a very important question when you try to do auto-formalization, maybe undergraduate, graduate level mathematics, research level mathematics, where maybe some objects are not in MathLib, you need to auto-formalize them. Some of them are there, and you really want to reuse what's already there, because you don't want to have something kind of, in its own little space. So that's a little bit for future work to kind of understand how to make sure that we reuse things well for MathLib. For high school, there was no real problems like this that came up. Yeah.
Okay, on that note, let's thank Thomas for